Well, since there's been news about a Chinese nuclear plant gas leak, I wanted to talk about that since I'm a bit of an expert. And I also wanted to talk about the Chinese nuclear leak and the noble gas problem in general. And for those that have watched videos about my history, I used to work as the manager of radioactive material licensing for the state of Texas. And as part of my duties there, I was part of the emergency response team. And I also worked as a radiological control technician for the U.S. Navy as a civilian in my younger days. So I have experience with nuclear power plants. And in terms of my state duties, I did accident assessment. I was liaison at the State Operations Center where the mayor would be, or where the governor would be in the event of a radiological emergency. So I have training from the Nuclear Regulatory Commission in responding to nuclear accidents of worse types than this. This is not an accident, but I'll get into that in more detail. Now, talking about the gas problem, and the noble gas problem in particular, when a fission reactor is operating, it produces helium, krypton, and xenon, and lesser amounts of neon and argon. The helium primarily comes about because there's alpha particles, and the alpha particles are helium nuclei. Well, they eventually get electrons attached to them and they become helium gas. So the fuel capsules and fuel rods fill up with helium gas. And then the uranium and plutonium or thorium, whatever the fuel is going to split roughly in two. And that's going to generally produce two lighter nuclei, about half the size, and also some smaller nuclei, like the helium nucleus. And so you get xenon and krypton isotopes of all types as some of those isotopes that come out of the fission process. And some of those isotopes are radioactive. And but you have this issue where the helium, krypton, xenon builds pressure. And you have a ceramic capsule generally containing the oxides of your uranium or plutonium, whatever your fuel is, or mixed fuel. So the ceramic capsules can rupture, they can crack, they can leak the gas. And then in many cases they have a small metal pellet around the ceramic capsules, although you can have ceramic capsules without a metal pellet. And those are welded, but they're susceptible to cracks and the welds are susceptible to failure. And then you put these capsules into rods and you can have fuel rod failures. Once again, the welds can fail or the metal can crack. You can get fatigue from the neutron exposure over time, or you can have metals where you have crystalline flaws due to the way the metal was fabricated. If you don't have the most pristine, best alloys made in the world, then they're susceptible to cracking, and sometimes those aren't picked up when you do x-rays of the material to try to prevent using crack-prone material. So what happens is, as I like to think of it, is keeping the noble gases in is like trying to suppress a fart. They're going to get out eventually. Now, if you have the best engineers and manufacturers in the world, it could take hundreds of years, and that's in an ideal case. And you also have the primary containment, which in the case of a pressurized water reactor like this, you have high pressure, high temperature water that's kept in the water state. And so you'd have to rupture that containment. But after the fuel's removed and after it's cooled off in a cooling pond for a certain number of years, it would go into a cask. And those casks are generally going to be attempted to be airtight so you don't have leaks. And then eventually the cask would be put into a long-term storage facility, which also is supposed to be leak resistant as a geological formation, but most geological formations are only so leak resistant. But that's generally not a big problem, and I'll talk about why. But one of the first things to know, if there is a Krypton and Xenon leak, as has been indicated inside the reactor, even if that were to escape, Krypton and Xenon don't form compounds in the human body. They do form some rare compounds, but it's not going to be appreciable enough in the human body to worry about. So when you measure the dose rates from Krypton and Xenon, the external dose, whatever you're measuring in the field dose out here, is exactly the same as your body is going to get all throughout your body. So you don't have to worry about long-term exposure. If you had strontium-90, for example, which can come from a reactor, that binds with the bones, and so it can give you a much longer-term bone dose because strontium is similar to calcium chemically. And even cesium-137 forms salts, and even though cesium-137 has a shorter biological half-life, the half-life is in a matter of several days or a little over a week at least. So you can get higher dose because it takes a while for your body to eliminate the cesium. But with the case of Krypton and Xenon, you don't have to worry about that. You breathe it in, you breathe it out, and you don't have that much dose. Now, in terms of the way the nuclear plant's designed, this fuel failure, the fuel pellet failure, fuel rod failures, they happen. So when you have damaged or leaking fuel rods, you want to deal with that during an outage when you're doing the refueling. And during the refueling, you can try to remove those rods, move them over to the cooling pond. The cooling pond also has ways of dealing with the leaking Krypton and Xenon because they're sealed and kept under negative pressure in that area. So these are all things that are dealt with in the design. And so it's not a problem, and in the US, if only 5 fuel rods had some minor damage or minor leakage, as has been indicated by the Chinese authorities, it wouldn't even get reported in the news media. So if that's all it is, it's not a problem at all. It's just something that's designed into the nuclear power plants because it's unavoidable that there's going to be some leakage. And that's why you're hearing from some of the outlets that there's no problem. If you have a leakage, that leakage of the primary coolant system or primary containment is a secondary problem. And that's why we don't see nuclear plant leaks all the time, because you have each step. You have the metal capsules, the metal rod, you have the primary containment, then you have the secondary coolant, because they use a steam generator where they run the hot water through a generator that develops steam on the secondary side, which runs your turbine generators to generate electricity. But those two bodies of water in the primary and secondary side are kept separate, or they're supposed to be. Now, some designs of steam generators can leak, and if they leak to the secondary side, they can cause overpressurization and pop relief valves. And then in addition to that, you also have a primary containment building in a lot of modern pressurized water reactor, where you see this big building that's made out of concrete with reinforced steel. And it's designed to hold a large amount of pressure so that if you do have a primary coolant leak, it's designed to handle a lot of the pressure. Now, it is possible in very extreme cases that you would still have to release to the environment. But in order for that to occur, and these are things that we drill all the time in the nuclear power business, you have to have multiple errors, one on top of the other. And each one is increasingly unlikely. So the idea that people are saying, well, there's a leak and there's krypton and xenon outside containment, that's highly unlikely. If they mishandled and allow the relief valve to go off or another valve to rupture inside containment, they may have a small amount of krypton and xenon inside the primary containment. But even that's not going to be a problem. People don't generally go into the primary containment building during operations. So they keep the area sealed off because the radiation dose rate's too high. So all of this is saying it's not a problem. And unless we're being lied to, and there's some additional information the Chinese government's not giving us. And I mean, that's possible, but based on all the publicly available information I've been able to read so far, this isn't a problem. Now, I did want to discuss the krypton-xenon issue in a little more detail. There's a number of isotopes that are stable long-term. They don't decay at all. And then there's 3 isotopes that have a half-life of greater than 10 to the 21 years, which means they're effectively stable and they don't contribute to the external dose ring. Then there are many, many isotopes that decay in less than a second or less than a few minutes, and so those decay so rapidly that they would normally decay inside the primary containment, and so we never see them escape and never have to measure them. So what we have left is a small number of isotopes of concern that we have to consider. One was krypton-85. It has a 10.8 half-life, 10.8 year. So in health physics, we use a fudge factor of letting it decay by 10 times its half-life. In reality, if it's really a large amount of material, you may have to go a bit longer. But 10 will give you an idea. So a ballpark idea of you need to contain it for 110 years. And now there's krypton-81, which has a 23,000 year half-life, so that would be 230,000 years, except that we can compare that to other isotopes like carbon-14, which has 5,730 year half-life, potassium-40 with a 13 billion year half-life, iodine-129 with 16 million year half-life. Those are all things that we have within our body. You've probably heard of carbon-14 used for dating, for carbon dating of the age of biological material, because we can measure the amount of carbon-14, determine what it had originally, and figure out how old it is. And these isotopes are so long-lived that they're actually just a minor source of radiation. So krypton-81 is not really a problem, especially since it doesn't form compounds within our body. Then you have things like krypton-77 and 87, which have about a 75-minute half-life, so that's 12 and a half hours. So that would only be a problem usually within the confines of the plant and the immediate areas surrounding the plant within a kilometer or two or a mile or two. So you generally aren't going to see exposure from that unless you have an accident where there's escaping material, and even then it's not a problem for long. You have Xenon-127, which is 36.3 days, so roughly a year it can linger, and that can give you a little more exposure. You have Xenon-131, which are 5.25 days, so for 53 days it can give exposure. So, and then Xenon-125, 16.9 hours, so you're looking at about 8 days. And there's also isotopes like iodine-131, which has an 8-day half-life, so it's around for like 80, 90 days. So there's a range of isotopes, and some of them are a problem for a longer time if they were to escape. In most cases, these are going to decay down to nothing within the fuel rods and capsules, and they're never going to escape. They're going to decay to something more stable, and that's where they'll stay. So that can give you an idea of what we're dealing with. We have, even with high nuclear waste, the Krypton and Xenon isotopes are pretty much gone after 100 years, or they have such a long half-life that it's not a problem. So that's why we can have the noble gas problem with Xenon and Krypton, but it's not really a problem long term, as long as we keep it encapsulated for around 100 years. And so I hope you learned a little bit about the problem, and hopefully the news media accounts are just overblown, and all there is just a minor amount of problems with the fuel cladding and fuel pellets leaking a little bit of Xenon and Krypton, which happens in every single reactor. So it's not a real problem. And so that's what I'm hoping. And like I said, I hope you learned something about the reactor problems. And if we hear more, I'll do an updated video on it. So thanks for watching. Please be sure to like, share it with your friends, and subscribe for my other videos. I'll try to get back to doing more theoretical physics videos in my next one. And so thanks again. Bye.